Hello, my name is Chris Reynolds. I'm going to talk to you today about containerization at Diamond Light Source. So first up, what is Diamond Light Source? It's the UK's national synchrotron, and it basically functions as a giant microscope. And we use synchrotron radiation to image matter of various kind of types. From crystal structures, meteorites, you name it. This has got to be a computer-generated photo because the sun is shining, and there's even car parking spaces. This is an aerial shot. The facility is located about 25 minutes south of Oxford. This is a kind of exploded view of the internals of a synchrotron. It kind of starts off in the middle with a linear accelerator, which is, if I have this part here. And then there's something called a booster ring here, where electrons are basically accelerated up this linear phase and rotated around the booster. And then they eventually land in this storage ring where they are kind of compressed and focused by these green bending focusing magnets, and eventually they're bent off into these beam lines using these red bending magnets. Once they enter the beam line, you can see there's a little optics hutch, and then there's an experimental room at the end where visiting scientists will come along and place their sample somewhere in the beam, and then they will effectively take images of that sample. There is some kind of feedback phase where they're interacting with our HPC resource, which I'll talk about in just a second. So here's a kind of a view during shutdown. We have around 5 shutdowns a year where we can do maintenance on the machine and also on the computing infrastructure. So this is where you can see these concrete, I think they're around 10 tons, these concrete blocks have been taken off the storage ring, which is the kind of big ring on the outside where electrons are doing laps. And you can see some of the magnets inside here. This is actually an I-beam line, which means that it has an undulator that effectively increases the energy of this particular beam line. And you can walk around when the machine is in operation. These blocks here are actually replaced. This is a no-go zone, and you can walk around the top of the accelerator. Here's an example of a detector. So once the beam has been bent off inside, come through an optics hutch, it's basically traveling down this metal tube here, and the sample was placed in a detector. So on the day that I actually took that photo, they were imaging cement just to try and understand its properties and how it absorbs radiation. So they're looking at burying radioactive waste, and they were looking at the physical properties of that of cement on that day. So some numbers. It's a 24/6 operation, and we have around 5,000 beam time hours a year. There's 9,000 visits per year, so typically scientists come in, they will spend some time, typically overnight, getting beam time on one of the 30 operational beam lines. In addition to that, we have 6 operational electron microscopes as well. We produce around 60 terabytes per day, and currently there's around 17 petabytes in our archive. So quite large data rates. We recently have installed a new cluster, which we've named Hamilton, after Margaret Hamilton, who was a software engineer who worked on some of the Apollo missions, and she coined the phrase software engineering. And you can see some numbers associated with that. So 2,500 CPU cores, 160 GPUs. So some reasonable run. Planning for Diamond 2 is underway. So that's a kind of complete replacement of the machine's internals, new detectors, higher data rates. So we really have a data deluge on our hands. So what about containers? Well, first it's kind of useful to understand what exactly the kind of workflow is at Diamond and the way that we engage with computing resources. So at one level there's some HPC resource. So it's a Univa Grid Engine cluster, and that's used for in-experiment data processing. So when the visiting scientist has their sample in the detector, they will typically take some images of that sample, and then they might want to explore a particular feature or rotate the sample in some way, and that requires some HPC resource. So they'll submit a compute job and expect the results to be back in the order of minutes. So we make use of queue subordination for that kind of stuff. We use some GPU cluster nodes for post-processing, so that's typically after the scientist has left. They might log in after they've left to process their data, which typically resides on the storage systems for around a month or two afterwards. Much of that HPC is utilizing software that, it's a very similar story to what everybody else has been saying, in that there are complex software stacks and dependencies. And a prime example of that is Savu, which is a tomography application. So I recount a discussion with the developer of Savu, and he explained to me that he drove all the way to Leeds on his day off to install Savu on some compute infrastructure up there. Stayed overnight just so that he could help with that, the scientists there actually get it working. And I think, if you were to do that multiple times, it just doesn't really scale. So it's quite complicated and requires some expertise to actually install. So HPC isn't the only area that's kind of container suitable, if you like. We've also got a fair amount of stuff that goes towards operating the machine. So, monitoring of our infrastructure. So we have a lot of servers, x86, that prop up the operation of the machine, control servers, etc. So we need to obviously monitor all of that, and we collect metrics as well. So from various different sources, we've got cluster statistics. Even things as simple as remote login applications. We use No Machine. We collect metrics on that. So, how many sessions are there in ongoing? And the last one is web apps. So Savu, our tomography application, there's a lot of, it's not the only one, there's a lot of kind of desire now from developers of the applications to present those as a web application. So rather than users interacting with QSub-like tools and interacting with the cluster, they log in through some front end, and they can submit to the cluster on the back end. Lastly, the CI/CD pipeline. So we make use of GitLab, and we use that for our configuration management. So typically what happens is that somebody managing infrastructure will take a branch, a master, they will make some change, perhaps update some component of the infrastructure, maybe like the host name of something, or some license files for an application. And as soon as they commit and push that branch upstream, it kicks off a CI/CD pipeline that's spun up inside a container, and basically does a linting check of the configuration management tool, which is CF Engine in this case, and just does a check that it's syntactically correct, etc. So in terms of deployments at Diamond, everything is pretty alpha, let's say. It's all in a testing phase. So we have a small Rancher Kubernetes deployment, and that runs our monitoring infrastructure. So Brancher is a kind of flavor of Kubernetes where you get something like an app store. So with a few clicks of a button, you can install Nginx, and we actually install Grafana, which allows us to graph up a lot of our metric data. And it also acts as a backend for the GitLab as well. And more recently, it actually acts as a kind of Kubernetes, an on-prem Kubernetes API endpoint for developers who are looking to build kind of backends for their front-end web apps. On our new cluster on Hamilton, we've got Docker job scheduling using Univer Grid Engine. So you basically make a resource request to Grid Engine and say, I want Docker and this Docker image, and it will schedule the job for you. And what actually it does is it runs the SG shepherd process, which is the kind of parent process of the job inside the container. There's a kind of good blog on the Univer website if you're interested. It will show how that works. They do have some support for bursting out to clouds as well using a product called NavOps, which we've tried, but it didn't work so well. Like most of you, we did some benchmarking of Singularity, and that's available to the cluster as well. So we're seeing a slow kind of uptake in the usage of this kind of stuff. Jupyter Hub as well. I sat down with a Google engineer a few weeks ago, and within about 20 minutes we had a Jupyter Hub up and running on Google's cloud platform. It was really quite easy. It's going to be a little bit more challenging when we come to deploy that in production, because the back end for Jupyter Hub is kind of easy if you're just running the notebooks, which is the kind of logged in user processing or processes that they fork inside containers on a Kubernetes cluster, but running in the cloud. But when they actually need access to data to process, and potentially a little bit of grunt as well, then things get a little bit more tricky. So they've expressed desire to run on our cluster nodes. So that's something that's a project that's more coming up than actually deployed. And the last one I put there is Openshift, because this represents a kind of interesting deployment for us in some respects. It was a developer who wasn't getting enough traction inside Diamond in terms of being able to deploy his application at the rate and the speed that he wanted. So he basically hired a few contractors and went and engaged with a data center in Vern in Iceland, and built an OpenShift layer on top of what was an OpenStack cloud. So we have some kind of expertise on setting up OpenShift, but it comes through this contractor. So it's not ideal, and it's something that we're looking to bring back inside Diamond. So what are the challenges for us going forward? Well, just in our kind of dipping our toe in the water, if you like, with what we're doing with containerization, these are the things that kind of sprung to mind as challenges. So the first one is kind of creating and managing Docker files and containers. So we have a registry. There are a few questions on our mind. For example, how do we keep track of security patches within those containers? So we use VMware Harbor for this, and we're investigating methods of being able to scan images in the repositories just to make sure that they don't contain any known vulnerabilities. The kind of creating and managing of Docker files, we've made good use of HPC Container Maker that NVIDIA presented yesterday. I used it to deploy HPCG and a few other bits and pieces, and it seems to work pretty well. And I think it would be better if it had a larger library of recipes contributed from the community. Unprivileged users needing to build and run containers. So that kind of ties into Canico, which is a Google tool which claims to be able to allow you to build containers without using root. And the way they do that is essentially you submit the build job to a Kubernetes cluster which builds for you. We haven't experimented with that. It's kind of on the list of things to try. And from yesterday, Scilab's remote builder, builder from Red Hat. I think IMG was another one that was mentioned. So these are very much on our list of things to try. As is the container orchestration tools. So, everybody knows about Kubernetes, but which Kubernetes do you go for? We've had a little play with Rancher, seemed okay. We had a few kind of catastrophic failures of it, which kind of burnt us a little bit. Google have an offering called Cloud Services Platform, which is coming out. It's in beta and is coming out sometime in April, which is kind of interesting. It's very much a kind of hybrid approach where they will have a Kubernetes managed deployment running on their public cloud and a managed Kubernetes deployment running on your x86 infrastructure, and they will manage the whole thing for you. So that could be an option for us, and also Openshift. That's another possibility. We run Red Hat internally for pretty much everything, so Openshift kind of might make sense. So those are the kind of challenges that we're looking at going forward, and those are the possibilities. Thank you. Any questions?